So we're going to look at problems that are called related rates problems. And the best way to introduce these is by using an example. So I'm going to use this as my example. Let's say we have gas in a closed container and it's being compressed slowly. The ideal gas law tells us that when a gas in a closed container is compressed slowly, its pressure, P, and its volume, V, are related by the equation P times V equals a constant. Now, what this means, you don't need to be able to do this in order to do related rates problems. What this means is if we were to graph pressure and volume on axes like this, that there's an equation that looks like this. As the volume decreases, the pressure is going to go up. And as the pressure goes down, the volume will increase. So we have this simple relationship between pressure and volume. But let's say I add some extra information now. Let's say I say we're going to start compressing this container of gas. We'll say initially the container has volume 100 cubic centimeters and the pressure is 1 atmosphere. So the gas is under atmospheric pressure and this container has volume 100 cubic centimeters. But now we begin to compress it. And here's the thing, we're going to compress it at a particular rate. We compress the container reducing its volume by, let's say, 0.2 cubic centimeters per second. So we're compressing it very slowly. We're pushing down very gently on this. So what's going to happen is, of course, we are compressing the volume. So the volume, we know that the volume is decreasing here. We're compressing the container and reducing its volume by 0.2 cubic centimeters per second. But since it has to follow this curve, the relationship between pressure and volume, the pressure is going to have to go up. And we can see if we look at this curve that initially the pressure is not going to increase very quickly, but later on the pressure will increase quite quickly. That's hard to say. So I can ask a question. When the volume is, let's say, 80 cubic centimeters, so we've been compressing it slowly, and when it reaches 80 cubic centimeters, how fast is the pressure increasing? I'm going to lock the focus on this. This isn't worried about this focus shifting around here. Usually I do this beforehand, I just forgot. There we go. Okay. So when the volume is 80 cubic centimeter, how fast is the pressure increasing? Here's how we set the center problem up. We've got this equation here. Pressure times volume equals constant. And if we look here, we have a known rate, which is, we know the rate at which volume is decreasing. And we can see this is a rate because it's cubic centimeters per second. And then we have an unknown rate. How fast is the pressure increasing? So we can write down calculus symbols for these. This is how fast the volume is decreasing, and then we know this. The volume is decreasing at 0.2 cubic centimeters per second. So this tells me what dV dt is. This is the rate of change of volume. And the problem is telling me that it's minus 0.2 cubic centimeters per second. And then we have an unknown rate that we're trying to figure out. How fast is the pressure increasing? So this is the rate of change of pressure. And this is what we're trying to figure out. What is dP dt? This is why these are called related rates problems. We have a known rate, dV dt, and we want to figure out an unknown rate, dP dt. Some other problems may have more than one known rate. So this equation doesn't have any t in it. So where are we going to get these dp dt's and dv dt's? Well, we're going to take derivatives with respect to time. This is going to be implicit differentiation when we take these derivatives here. I know that both pressure and volume here depend on time. They're both changing. The volume is decreasing, the pressure is increasing. And so I can use this equation and implicit differentiation to get the relationship between dv dt and dp dt. So here's how we do it. We already know how to do it because we know how to do implicit differentiation. Here I have pressure times volume is constant. That's my equation. And what I'm going to do is I'm going to do time derivatives of both sides. Squeeze in a little d dt here. So this is saying I'm going to take the derivative, but time is my variable here. And these are both hidden functions of time. This side is straightforward. This is a constant. Constant doesn't depend on time, so that derivative is going to be 0. But here, both pressure and volume are unknown functions of time. Since they both are functions of time, I have to use the product rule for taking the derivative of this. So I use the product rule, I get the derivative of p, which I don't know, so I'll just write it symbolically. dp dt times volume. Then the second term from the product rule, I get the derivative of volume, dv dt times p. That's the product rule. Now, once I've taken these derivatives, I can go back and start looking for information to plug in to try to solve for the unknown rate. So let's look at what we can figure out here. This is my unknown. This is what I'm trying to solve for. So that means I need to figure out v and dv dt and p at the point when the volume is 80 cubic centimeters. Two of these are straightforward. When the volume is 80 cubic centimeters, so that means I'm going to put 80 here. As a side note, I couldn't put 80 in up here because that would mean volume. We're treating volume as if it were constant, and its derivative wouldn't work. Volume is changing, so I'm going to have dv dt here. But after I've taken the derivatives, then I can plug in 80. So let's continue. dv dt, do I know that? Yes, it's up here. Reducing its volume by 0.2 cubic centimeters per second. So this is a minus 0.2. Notice it's got to be negative because the volume is decreasing. I'm going to do minus 0.2. I'm not going to chase the units around. The units will all work out. This is my unknown that I'm trying to solve for, dp dt. So the only tricky one is how do I get pressure? And the way I get pressure is I come back to this equation. Pressure times volume is constant. At the start, the pressure was 1 atmosphere and the volume was 100 cubic centimeters. So that lets me figure out this constant. At the start, P was 100, or P was 1 atmosphere, volume was 100 cubic centimeters. So that means P times V was 1 times 100. So that's my constant. Now I know the 100 is the constant. Doesn't change. Now V is 80. What's P? Well, P times 80 has to be 100 because it doesn't change. So that means P is 100 divided by 80, which reduces to 5 over 4. Oops, you can't see that. Okay? So that plugs in here. This equals 0. So now I have a bit of algebra to do to figure out what dp dt is. So let me see here. This is 1/5 or minus 1/5 times 5/4. So dp dt times 80. This is negative 1/5 times 5/4. That's negative 1/4 equals 0. I'm running out of space down here. If I add the 1/4 over, then divide by 80, dp dt is 4 times 80 is 320. And then my units for pressure in this problem were atmospheres. And my units for time was seconds. So this tells me that at this point in time, when the pressure had been reduced to 80 cubic centimeters, and I was compressing the volume by 0.2 cubic centimeters per second. At this point in time, the pressure is increasing, notice this is positive, at a pretty small rate, 1 over 320 atmospheres per second. And if we were to put in a different value here, we would get a different rate for that. So that's my first example. I want to do one more example, and almost all of your related rate problems are going to be what I call geometric related rates problems. Most of the related rate problem that you'll see, they will not give you the formula like PV equals constant like the last one. You'll have to derive that formula on your own. So I've stolen this acronym, DREADS, from Patrick JMT, and I have several other of his videos that I have linked on the class calendar with lots of examples of related rates problems. So I've just stolen this from him. So this is his acronym for the steps to do when you're doing a geometric related rates problem. So I'll go through this briefly, and then we'll flesh it out with this example down here. So the first thing you're going to do with a geometric related rates problem after you read the problem is you're going to draw a diagram. You're going to draw a picture. This is geometric, and so presumably there's going to be some picture that you can draw that describes that pictures what's happening in the situation. And I'm going to add to this, you're going to label, and you're going to put numbers on things that are constant, and you're going to put variables on things that change. It's very important that you do not, you'll be given information, like if you go back, let me go back to this previous problem, where when the volume is 80 cubic centimeters, the volume is changing. So this is like specific information. At a particular point in time, the volume is 80 cubic centimeters. You wouldn't want to put 80 into this formula because volume is changing. It's not until after the derivative that you can plug 80 in. That's the point of this caveat. When you make your diagram, things that are constant, you're going to put numbers on, but things that vary, you have to put variables on so that the derivatives work correctly. This first step and the third step are often the hardest steps in the problem. The derivatives are not necessarily that difficult. The next is you're going to locate the rates in the problem. And you should be able to identify using d something dt notation. Typically there's one unknown rate and one known rate, but sometimes there can be problems with more than one known rate. But you should be able to identify them using the variables that you've inputted on the diagram. Next, you're going to write an equation. And the equation is going to be geometric in nature. It's going to come from the geometry that you've drawn in the diagram up here. You'll see down below. Once you've got the equation, oh, and by the way, you should eliminate any variables where you don't care about rate. Next, you're going to take derivatives. This is going to be implicit differentiation, ddt. So they're going to be time derivatives, and everything that's varying, you have to remember, is a function of time. You have to use implicit differentiation. And then you're going to substitute specific information and solve. So this is his DREADS acronym: diagram, rates, equation, derivatives, substitute specific information. Let's go through this tricky problem using this. And on the class calendar, I have linked several more examples that he's worked out in very common textbook situations that you'll see. So here's the example I'm going to do. A tank is in the shape of an inverted cone. It has radius 10 and height 20 meters. Water is being added to the tank at 3 cubic meters per second. How fast is the height increasing when the water is 16 meters high? All right, so following my acronym, first I want to do a diagram. So this problem tells me I have an inverted cone, so it's an upside down cone, looks something like this. So let's draw a nice picture of it. And what I know about it, it's got radius 10 and height 20. That means its diameter is 20. So it's about the same distance across as it is its height. So I'll try to make it look somewhat correct. So there's the top. It's that far across. It's going to be about that far down. There's my cone. I'm going to label numbers on things that are constant and variables on things that vary. Well, what do I know that's constant? Well, I know the radius is 10. That doesn't change. 10 meters. And I know the height is 20. What's varying? What's varying is water's being added to the tank. So water's being dumped into this tank. And as it goes in, it fills and makes a smaller cone on the inside. So I have another cone inside here. That's the surface of the water as we're pouring water into this tank. Now this cone also has a height and it has a radius, but those are changing. As the water fills up the tank, those vary. So even though I have this when the water is 16 meters high, that's not a constant. That's something that's varied. This is a specific information that we're going to substitute later. So that means I'm going to label these with variables. I'm going to use sensible variables. This is the height and this is the radius. There we go. So H and R represent the height and radius of the conical pile of water, if you will, and 10 and 20 are the radius and height of the entire tank. So that's my diagram. So next, rates. Identify using d something dt notations. Let's look for the rates in the question. Let's see here. Water's being added to the tank at 3 cubic meters per second. So that's a rate. And you can tell by the units, this is a volume. 3 cubic meters per second. So I don't have volume yet in my picture. So that means I'm going to need to have a volume formula that will come to when I'm doing the equation. A sensible letter to use for volume would be V. So this rate is going to be dV dt. V is going to stand, of course, for volume. And this is telling me it's being added, so I'm going to say it's plus 3. And the units here are cubic meters per second, but I'm not going to worry about units. All the units match here. I'm not going to have to do any unit analysis here. The other rate, how fast is the height increasing when the water is 16 meters high? How fast is the height increasing? So there we go. There's my other rate. How fast is the height increasing? Height I do have in the diagram. Height is represented by the letter H. So this is dH dt. The rate, the height is increasing, and this is what I'm going to try to figure out. So these are the rates I'm going to have to relate. So I've identified the rates. Next, I need to write an equation, and I need to eliminate any variable where I don't care about their rate. So if I look at the rates that I have dV dt, which I know, and I have dH dt, my unknown rate. So that tells me I need an equation that relates V and H. And from geometry, and on AP they give you these formulas, and they also will be given on the homework. In geometry we learn how to get the volume of a cone. The volume of the cone is 1/3 pi r squared h. So there's my equation. This is H and R. It's the volume of this cone we're computing. I don't care about the volume of the entire tank. It's the volume of water in the tank that I care about. But there's a problem here. And this is the trickiest part of this problem, actually. We want to eliminate any variable where we don't care about the rate. Well, this has 3 variables: volume, radius, and height. But all I care about is volume and height. So I need to get rid of this R. I need to write R in terms of H. So I need R as a function of H. So I can plug it in here. I don't want R's in this equation. And this is where geometry comes and bails us out. If you look carefully in this picture, this is why I chose this example, because it's a tricky example. There are similar triangles here. This is 20, this is 10, and then here we have this right angle, and here we have a smaller version of this triangle. And because these triangles are similar, this tells me that since this radius here since the radius here is half of the height, everywhere as we go down, that will also be the case. So the geometry of the cone tells me that And the similar triangles tells me the radius is always 1/2 of the height. So that's going to go in for the radius. I get V equals 1/3 pi 1/2 h squared times h. So next I'm going to have to take derivatives, but I don't want to take the derivative of this as it stands. This is horribly ugly. So I'm going to simplify this. 1/2 squared is 1/4. Then I have a 1/3 out in front. Then I have pi. So 1/4 times 1/3 is 12. And then I have h squared times h cubed. So here is my equation. It relates volume and height. The unwelcome variable r has been eliminated because I don't have dr dt. I don't care about it in this question. Now, we're almost done. Next step, derivatives. So I'm going to take time derivatives, doing implicit differentiation, remembering that both v and h are functions of time. So that means I can say d dt v equals d dt pi over 12 h cubed. This just is dv dt. Pi over 12 is a constant. The derivative of h cubed is 3h squared. So I get 3 pi over 12 h squared, and then because of the chain rule I have to multiply by dh dt because h is a function of time. So this is the formula that relates volume and height. Finally, substitute the specific information and solve. So let's look at what we've got here. dv dt I know is plus 3. 3 pi over 12, that reduces to pi over 4. H, so my question says, how fast is the height increasing when the water is 16 meters high? So that's a height. That's h. So I'm going to put 16 squared here. And then my unknown that I'm trying to solve for is dh dt. And so I have to work out what this is. So I'll get out my calculator. 256 over 4 is 64. Then I divide by 64 pi, and finally I get dh dt is 3 over 64 pi, and this is meters per second. And I know that's meters because height's in meters, and I know it's seconds because dv dt was cubic meters per second. So the height's increasing pretty slowly at that point.